Sangro River, Italy, December 3rd through 4th, 1943. A flooded winter river cuts through steep clay banks. German observers watch from high ground above Torino di Sangro. At 2300 hours on December 3rd, 1943, Royal Engineers of 5th Corps lay out 10-foot steel panels by hurricane lamp. Their stacks are recorded in the 8th Army Engineer Situation Report for December 3rd through 4th. At 0600 hours the next morning, the logbook entry is specific. Bridge completed in 36 hours under hostile observation. Traffic commenced 0600 the span, approximately 200 feet, carries Churchill tanks weighing approximately 40 tons immediately. German staff tables for 10th Mountain Corps had assumed a minimum 3-day interdiction window. Reality was half that. The crossing prevents a pause, denies the enemy time to rotate artillery, and keeps the winter offensive moving north toward the Sangro-Arielli line. If one Bailey could reset a timetable by 36 hours, what would thousands, standardized, truck-borne, and assembled with hand tools, do to Germany's strategy across an entire continent? A prototype panel stands against a timber trestle at the War Office Experimental Bridging Establishment Test Ground in Christchurch, Hampshire. On a temporary table, calipers, rivet gauges, and a notebook labeled Panel Mark 1, 10 feet by 5 feet. The date is July 1940. Britain has just evacuated Dunkirk. Europe is falling. Pre-war British military bridging assumed methodical river works with cranes and specialist gear. After Dunkirk, the Directorate of Fortifications and Works notes a shortfall in summer 1940 planning minutes. Loss of mobility through bridge destruction exceeds equipment replacement capacity. Captain Donald Coleman Bailey, a civil engineer, presents a concept. Colonel Gifford Martel, a mechanization advocate, reviews it. Officers of Royal Engineers trial detachments test it under field conditions. Bailey's design is radical in its simplicity. Prefabricated welded and bolted steel panels, cord posts and transoms, standardized pins, decking with timber chesses, incremental buildability, single to triple truss configurations, launchable by roller and nose without cranes. By early 1941, tests show a 150-foot prototype. Approximately 40 men assemble it. It sustains approximately 70 tons with no permanent set. The War Office Experimental Bridging Establishment Trial Note from 1941 records deflection readings per load step. War Office file minutes from late 1940 authorized production in principle. By the first quarter of 1942, procurement spans over 600 firms across Britain. The bridge that fits on 3-ton lorries is on track to outpace German demolition schedules. A modular bridge that can be hand-built shifts bridging from engineer project to unit capability timelines compress from days to hours. Every infantry division, every armored brigade, gains the ability to restore mobility without waiting for specialized equipment or heavy machinery. The panels weigh approximately 570 kilograms each. 6 men can carry one. Transoms slot into place with hand tools. Pins secure joints in seconds. No welding, no cutting, no cranes. Just steel, geometry, and human labor. Germany still relies on heavier pontoon bridges and fixed-span equipment that requires transport by rail. Britain is building a bridge that travels by truck and assembles faster than the enemy can plan interdiction. A Wadi Gap west of Mechelai. Sappers count panels and chalk on a lorry bonnet. P112, T44, R16, the cooling tick of Bedford trucks under a desert night. The date is March 1942. The Africa Corps is advancing. The 8th Army is mobile, aggressive, and learning. Axis intelligence appreciates Allied pontoon capacity but underestimates repeatable, night-build bridging with no cranes. A captured report from an Africa Corps Pioneer Company notes. Enemy bridges appear overnight. 7th Field Company, Royal Engineers, and 8th Army Engineer Groups receive Bailey equipment via Egypt. Defensively equipped merchant ships flow panels through Mediterranean convoys. Each 10-foot panel weighs approximately 570 kilograms, man-portable by 6 soldiers. Standard transoms and rakers fit universal sockets. Launch noses guide spans across gaps. Roadway chassis are guided onto rollers with jacks. A destroyed Italian bridge near a wadi is replaced in approximately 18 hours. The company war diary records the timing. Intermittent air threat slows work but does not stop it. More than 20 armored vehicles cross under shellfire the following morning. The 8th Army Engineer log from spring 1942 documents erection times. Royal Engineer war diaries reference night work and dispersed crew drills to mitigate shelling. The bridge becomes tactical doctrine. Gaps become delays but short delays. Hours, not days. Within 6 months, approximately 80 Bailey crossings are recorded in North Africa. None fail in service. German engineers blow bridges expecting week-long interdiction. British engineers restore them in a night. Reliability turns into momentum. Field Marshal Erwin Rommel's supply lines stretch across hundreds of miles of desert. Every delay costs fuel, ammunition, and operational tempo. The 8th Army, by contrast, closes gaps faster than German intelligence can track. Tactical mobility becomes operational advantage. By June 1942, the Bailey is no longer experimental. It is standard equipment. Every Royal Engineer unit in theater carries the components. Every Commonwealth division knows the drill. Training is universal. Parts are interchangeable. Speed is doctrine. The Desert War is a war of movement. Armor raids, flank attacks supply interdiction. Bridges matter because they dictate tempo. Germany expects rivers and wadis to slow the British. Britain erases the delay with prefabricated steel and trained crews. The numbers tell the story. 80 bridges in 6 months. 0 structural failures. Average assembly time under 20 hours. Maximum load. Class 40 tons. Sufficient for Churchill tanks, Sherman tanks, and heavy lorries. Enough to keep an army moving. A stencil reads, single, double, triple, on a wooden crate. Foreman tally panels against a loading slip marked, to Southampton. Convoy, the date is mid-1943. Britain is preparing for invasion. Europe is the target. Mobility is the plan. Pre-war bespoke bridging gives way to wartime batch manufacturing. Germany expects interdiction to slow Allied armor. Britain aims to erase delay through industrial scale. The Ministry of Supply, War Office, and Royal Engineers Board coordinate a web of contractors, steelworks, fabricators, transport. Standardized sets emerge. Single, double single, triple single configurations. Class 40 through Class 70 loadings with built-up cords. Later, Class 80 plus with multi-tier trusses. Packing lists fit 3-ton lorries. Assembly by unit-level teams trained to identical drills. Monthly output climbs into tens of thousands of tons. Cumulative panel deliveries reach hundreds of thousands by mid-1944. Ministry of Supply ledgers track production. War Office planning tables show shipping cuts approximately 40% versus heavier fixed-span kits. Every panel stamped in Birmingham is identical to every panel stamped in Glasgow. Every transom from London matches every transom from Sheffield. Interchangeability at industrial scale. A bridge broken in Italy can be repaired with panels from England, Egypt, or India. The system is global. Training standardizes as well. Royal Engineer schools teach identical procedures. Commonwealth forces, Canadian, Australian, New Zealand, South African, Indian, learn the same methods. A Canadian sapper and a British sapper can build the same bridge using the same manual. Germany's bridging capacity depends on specialized equipment, heavy transport, and limited production. Air raids disrupt German factories. Resource shortages limit steel allocation. Training cannot keep pace with losses. The Wehrmacht's bridging arm shrinks while Britain's expands. A logistics organism emerges. Standardized parts. Global interchangeability. Predictable training. Proven drills. Speed becomes doctrine. Britain can assemble a 200-foot Class 40 bridge in hours. German field units still require heavier gear and more time for equivalent spans. The contrast is stark. One side builds faster than the other can destroy. One side's factories outpace the other's demolition teams. One side trains thousands of engineers while the other struggles to replace losses. By December 1943, the Bailey is not just equipment. It is a system. It is infrastructure. It is operational doctrine. And it is about to land in Europe. A folding rule clicks shut. A sapper marks bank heights with a grease pencil while smoke from artillery drifts across reed beds. The date is March 16, 1943. Southern Tunisia. The Mareth Line. German-Italian defenses rely on deep wadis and blown culverts to slow the Eighth Army. German and Italian planners assess significant delay to heavy vehicles. Deep wadis cut the landscape. Culverts are demolished. Artillery observers watch every crossing point. The plan is attrition through geography. Field Marshal Albert Kesselring's staff estimates minimum 5 days delay per major crossing. Reality proves otherwise. 8th Army Engineer Report 8/43 documents 13 Bailey spans in 5 days. Average assembly time, approximately 4 hours per span. Under harassment fire. Under observation. Under shell fire. The wadis range from 30 feet to 120 feet wide. Each requires different configurations. Corps and divisional field companies execute the work. General Bernard Montgomery's operations staff coordinates the timing. German Panzergrenadier elements report shellfire interdiction attempts, but the bridges keep appearing. Italian artillery units, low on ammunition, cannot sustain fire. German batteries shift priorities hourly. Span choices are keyed to bank conditions. Double single for medium load on firm banks. Triple single where ground is soft. Rapid launch from roller trestles. Pre-cut chesses for decking. The engineer appendix notes that primary failures are limited to superficial panel hits. Crews carry spare panels and pins to swap in minutes. One span takes a direct hit, repaired in 40 minutes. The night work is particularly effective. Royal Engineer Companies arrive at dusk. Reconnaissance complete by 2100 hours. First panels laid by 2200. By 0300, traffic opens. German artillery observers cannot adjust fire in darkness. Muzzle flashes reveal battery positions to Allied counter-battery radar. 8th Army Operation Order Annex, Engineer Section, dated mid-March, cross-references artillery fire tables versus working parties. Enemy engineer situation reports, captured later, note, rapid restoration, a captured Italian engineer log records. British bridges completed between darkness and dawn. Are demolitions effective for hours, not days? Supply columns cross 12 hours earlier than estimated. Armor infantry attacks synchronize with artillery plans and air windows. German countermoves arrive late. The timetable advantage compounds. 50th Infantry Division crosses Wadi Zigzag 18 hours ahead of schedule. New Zealand's 2nd Division bypasses expected choke points. The logistics multiply. Each hour saved means fuel conserved. Ammunition forward sooner. Artillery in position earlier. Infantry rested instead of waiting. The operational tempo accelerates beyond German planning assumptions. The saved 3 days across the operation equals the road time of an entire corps. Germany cannot offset that advantage elsewhere. Every hour saved at a wadi translates to fuel saved, ammunition forward, and infantry rested. The mathematics of mobility become overwhelming. The Mareth Line falls not because it is weak, but because it cannot stop what it was designed to stop: movement. Bridges appear faster than intelligence can report them. Crossings open before artillery can mass against them. Momentum replaces attrition. Geography becomes irrelevant. A German staff officer's diary, recovered later, notes frustration. British bridging tempo exceeds our demolition capacity. The statement is clinical. The implication is strategic. Germany is fighting an opponent who rebuilds faster than Germany can destroy. The defensive doctrine assumes static timelines. The reality is dynamic engineering. By March 28, the Mareth Line is behind the 8th Army. Approximately 13 Bailey bridges span the wadis. Traffic flows north. The pursuit continues. The offensive does not pause. Tunisia's days are numbered. A clipboard lists panels 130 tons. Class 40 spotters call artillery arcs while men guide panels under shrapnel hiss. The date is December 3, 1943. Sangro Valley, 5th Corps Sector. Winter rain swells the river. Water runs brown and fast. 10th Mountain Corps, German, intends artillery to deny bridging for several days. The plan is sound. The river is wide. The banks are steep clay, unstable and difficult. Observation from the high ground gives German gunners clear fields of fire. Every approach is registered. Every working area is pre-plotted. 5th Corps engineer diary logs completion within 36 hours. Approximately 500 rounds fall during the work. Minor panel damage only. Traffic opens at 0600, December 4th. The German plan fails against British execution. General Harold Alexander later comments on winter mobility in his dispatches. 5th Corps engineer staff execute the plan under fire. German Corps artillery commanders adjust fire tables repeatedly but cannot prevent completion. Counter-battery fire from British artillery suppresses some German guns. Smoke obscures others. But the work continues regardless. The bridge spans approximately 200 feet. Bank seats are cribbed with timber and steel pilings driven into wet clay. Roller plus launching nose method shortens exposure time. The bridge grows across the river in sections. Panels slide forward on rollers. Transoms lock into place. Pins secure joints. Crews rotate in sections to avoid fatigue. Sappers work through the night in 3-hour shifts. Hurricane lamps provide light, carefully shielded to avoid giving aiming points. Shellfire provides urgency. Near misses spray mud and shrapnel. Direct hits are rare but costly. One sapper is killed when an airburst catches him in the open. 2 more are wounded by shell fragments. The work does not stop. Casualties are evacuated. Replacements step forward. The bridge continues. 5th Corps G3 and G4 annexes document the timeline in meticulous detail. Survey complete. December 3, 1400 hours. Materials on site. December 3, 1800 hours. First panel laid. December 3, 2300 hours. Midpoint reached. December 4, 0200 hours. Traffic test. December 4, 0500 hours. Traffic opens. December 4, 0600 hours. Air photo reconnaissance frames show bridge completion. German fire plan sheets, captured later in January 1944, show targeting priorities, but the bridge holds. Priority 1, bridge approaches. Priority 2, bridge center span. Priority 3, traffic on bridge. None of the priorities prevent completion. The 5th Corps advance keeps calendar pressure on the Gustav Line. German artillery resupply lags the tempo of Allied repair. Every bridge built faster than expected compresses German reaction time. Every river crossed ahead of schedule forces German reserves to move prematurely. Strategic flexibility erodes with each crossing. The crossing time beats the enemy's shell replenishment cycle. Tempo becomes protection. Speed becomes armor. The bridge is completed not despite artillery fire, but faster than artillery fire can stop it. The mathematics favor construction over destruction. German doctrine assumes that sustained shellfire will interdict bridging operations for days. Doctrine based on First World War experience. Doctrine based on static fronts and limited mobility. British doctrine assumes that modular construction and trained crews will complete bridging in hours. Doctrine based on industrial capacity and standardized training. Reality favors the British assumption. A single bridge at Sangro does not win the Italian campaign, but it demonstrates a principle: mobility maintained under fire, logistics sustained under observation, operations continuing despite interdiction. The principle scales. What works at Sangro works at the next river and the next and the next. By December 5th, the bridge carries tanks, lorries, and artillery north. Churchill tanks, approximately 40 tons each, cross at regulated intervals. 3-ton lorries carry ammunition. Bren gun carriers ferry infantry. The traffic is continuous. The winter offensive continues. The Gustav Line draws closer. Germany's defensive strategy depends on rivers as barriers. Britain is proving that rivers are merely appointments on the engineer's calendar. The Sangro crossing becomes a case study. Royal Engineer schools study the operation. Training manuals incorporate the lessons. Future bridges will be built faster with fewer casualties using refined techniques. But the core principle remains: standardized equipment, trained crews, and execution under fire. A sniper's crack. Engineers freeze behind a transom beam. A corporal shouts the pin count and men push forward. The date is February 8, 1944. Route 6 corridor. Rapido River and Liri Valley. Monte Cassino looms above. Ancient abbey, modern fortress. Blown bridges. Mined approaches. Sniper lanes. German doctrine bets on long delay. The 1st Parachute Division holds the high ground. Every approach is covered. Every crossing site is registered for artillery. The town itself becomes a weapon. Rubble creates obstacles more effective than intact buildings. Royal Engineer Companies for 2nd New Zealand Division rebuild St. Angelo No. 2 Bridge on February 8 in approximately 5 hours under fire. Royal Engineer Report: opened 1700 hours. First tank 1725, 5 hours. Under sniper fire. Under mortar fire. Under observation from the monastery heights. 2nd New Zealand Division engineers execute the work with characteristic efficiency. Polish 2nd Corps engineers take over later in the campaign as forces rotate. German 1st Parachute Division defensive notes describe rubble obstacles carefully placed to channel attackers into kill zones, but the bridges hold despite everything. Short and medium Bailey spans cross cratered masonry. Ancient Roman foundations become modern abutments. Abutments are shored with salvaged stone and timber from destroyed buildings. Engineers scavenge materials from ruins. Church timber becomes decking supports. Palazzo stone becomes cribbing. Deck sections are replaced repeatedly under shellfire. A mortar round hits the bridge at 0900. Sappers replace damaged chesses by 0940. An artillery shell strikes at 1400. Repairs complete by 1530. The cycle repeats daily, sometimes hourly. The casualty log records 4 killed in action, 9 wounded in action over 3 months. Sapper William Thompson, age 23, killed by sniper fire while securing a transom pin. Lance Corporal James MacDonald, age 27, killed by mortar fragment while laying decking. Sapper Harold Price, age 19, killed by shell blast on approach road. Sapper Robert Chen, age 25, killed by mine while surveying bank conditions. 9 wounded, shrapnel, gunshot, concussion, burns, crushed limbs. All evacuated, all replaced. The work continues. The bridge remains functional through fluctuating front lines until May. 2nd New Zealand Division engineers war diary documents the timeline day by day. Air photo series shows progressive destruction and repair. Images taken weekly show the same bridge destroyed and rebuilt repeatedly. German strongpoint sketch maps show bridge locations marked as priority targets with notation, daily interdiction attempted, limited effect. Even where the city becomes rubble, the road remains functionally restored. Artillery and armor can be fed forward nightly. Ammunition trucks cross under darkness at regulated intervals. Supply lorries return with wounded. Ambulances use the bridges both directions. The bridge is not comfort, it is function. Cold function in a landscape of devastation. Monte Cassino does not fall quickly. For major offenses from January through May. The Abbey is bombed on February 15th. Controversial decision. Limited military effect. The town is shattered by artillery. Thousands of shells daily. Soldiers fight house to house, room to room, stone to stone. Parachutists against infantry. Experience against determination. But through it all, the bridges function. Damaged at dawn, repaired by noon, damaged at dusk, repaired by midnight. The engineers become as much combatants as builders. They wear helmets constantly. They carry rifles. They dig slit trenches beside their work sites. They fight when attacked. They build when fighting pauses. A German report, captured in May, notes, Allied bridging is continuous despite interdiction efforts. Continuous. The word is key. Not occasional. Not intermittent. Continuous. Germany shells the bridges. The bridges are repaired. Germany shells them again. They are repaired again. The cycle cannot be broken. Artillery observer reports show frustration. Bridge struck 0800. Bridge functional 0900. Bridge struck 1200. Bridge functional 1300. The timestamps document futility. Destruction is temporary. Repair is inevitable. Destruction denies comfort, not movement. The bridge turns ruins back into a route. Monte Cassino falls on May 18, 1944. Polish troops raise their flag over the monastery ruins. The bridges are still standing. Battered, patched, reinforced, but standing. Traffic still flows. The offensive moves north toward Rome. The cost was high. Thousands dead in the battle. Hundreds of engineers killed or wounded maintaining the bridges. But the bridges held. And holding meant winning. Because mobility sustained means offensives continue. And continued offensives mean eventual victory. A chalkboard at an engineer park lists sites. Benouville 90 feet, 1400 hours. Vire tributary 120 feet, 2200 hours. The date is June 1944. Normandy. Orndives Vire River Systems. D-Day and beyond. The liberation of Europe begins with beaches and bridges. German command expects marshes and blown crossings to slow the breakout. The bocage country, hedgerows, sunken lanes, small fields, is natural defensive terrain. Every stream is an obstacle. Every culvert a choke point. Every bridge a target. The defensive plan is comprehensive. Assault divisions land with complete Bailey kits, approximately 64 truckloads per unit. The bridges land with the infantry, pre-packed, pre-planned, ready to deploy. Each division's engineer battalion carries sufficient equipment for 6 to 8 Bailey bridges ranging from 60 feet to 200 feet. The planning is meticulous. 6th Airborne Sector near Benouville receives priority. Pegasus Bridge is captured intact in a glider assault, one of the war's most daring operations. But other crossings are destroyed. Royal Engineer Field Squadrons execute the work. General Miles Dempsey's 2nd Army Engineers coordinate across sectors. The bridges appear as planned, sometimes ahead of schedule. Benouville 90-foot Bailey in 2 hours 30 minutes. From first panel to traffic opening. Survey to completion. The speed astonishes German observers. Extension at Tilly-sur-Seulles to approximately 180 feet for Sherman DD tank traffic. The amphibious tanks need reinforced approaches. Engineers add cribbing and strengthen abutments. By July, more than 1,000 Bailey structures span Normandy. The number is staggering. 1,000. Ranging from 30-foot culvert replacements to 200-foot river crossings. Less than 1% recorded structural failure. The reliability is absolute. German demolitions become engineering appointments, not operational crises. SHAEF, Supreme Headquarters Allied Expeditionary Force, Engineer Situation Reports for June document the numbers in weekly summaries. 2nd Army Engineers daily returns track installations by division and corps. The bridges are not improvisation. They are pre-planned infrastructure executing on schedule. Each assault division carries standardized equipment. Each engineer battalion trains to identical procedures. Each squad knows the drill. The system is universal across British, Canadian, and American forces. A British sapper can assist a Canadian crew. An American engineer can read a British bridge plan. Standardization at scale. With bridges pre-packed and drills standardized, every blown span becomes an engineering appointment, not an operational crisis. The German demolition plan becomes a schedule for Allied engineers. Bridge destroyed at 0800. Survey complete 0830. Materials on site 0900. Assembly begins 0930. Bailey installed by 1400. Traffic resumed by 1500. Next bridge. A chafe note dated June 25 states plainly, Without Bailey bridges, the advance to Cannes would have ceased. 10th June. Engineering, not chance, preserves tempo. Planning, not luck, maintains mobility. The note is classified secret at the time, declassified after the war. The admission is stark. The hedgerow country of Normandy is designed for defense by nature and improved by German engineering. Narrow lanes channelize movement. Sunken roads create ambush zones. Small rivers and streams cut every approach. Every crossing blown by retreating Wehrmacht engineers. Every culvert demolished. Every bridge destroyed. Germany expects weeks of delay. Britain delivers hours of inconvenience. Canadian engineers in the Cannes sector build 42 bridges in June alone. American engineers, using identical Bailey equipment under Lend-Lease, build 63 bridges on the western flank by July 1st. Commonwealth engineers throughout Australian, New Zealand, South African units add dozens more. The system is universal. The result is mobility. British Second Army alone crosses 138 blown or damaged bridges in June using Bailey equipment. 1st Canadian Army, 96 crossings. The numbers are documented in post-campaign reports. Each crossing represents a potential multi-day delay converted into an hours-long task. By June 30th, the beachhead is consolidated. 7 divisions ashore. 15 more arriving. Supply dumps established. Airfields operating. The breakout is preparing. And every division, every corps, every army knows. Rivers are not barriers. They are engineering problems. And engineering problems have solutions that arrive by truck, assemble by hand, and function under fire. Germany's strategy depends on geography slowing the Allies. Natural obstacles, rivers, marshes, bocage, combined with demolition creating strategic delay. Allied strategy depends on engineering erasing geography. Prefabricated bridges, standardized training, industrial capacity, democratic mobilization, all focused on a single goal, sustained mobility. In Normandy, June 1944, engineering wins. The bridges appear faster than German intelligence can track them. The advance continues faster than German reserves can respond. The momentum builds toward breakout. And when breakout comes in late July, the bridges will ensure it becomes a pursuit, not a pause. Shrapnel sparks on a panel as an 88mm shell bursts upstream. A signboard reads Class 40, convoy distance 30 yards. The date is August 25, 1944. Vernon-Vernonnet crossing. The Seine River. The last major water barrier before Paris. The last geographic shield for Germany west of the Rhine. Wehrmacht plans to hold the Seine line for approximately 48 hours more. Every hour matters. Reserves need time to organize. Supply dumps need time to evacuate. Defensive positions need time to prepare. The river is wide, more than 250 feet at Vernon. The current is strong. The banks are difficult. Allied planners target multi-site crossings. 43rd Wessex Division builds an approximately 1,126-foot combination of fixed and floating Bailey in approximately 36 hours under shelling. The construction begins at 2100 hours, August 25th. Traffic opens at 0900, August 27th. 18 casualties recorded. 3 killed outright by shellfire. 15 wounded by fragments, concussion, and burns. Sapper Michael Brennan, age 21, killed by direct shell hit while positioning a pontoon. Lance Corporal David Williams, age 29, killed by shrapnel while securing deck chesses. Sapper Thomas O'Brien, age 24, killed by secondary explosion. The bridge holds despite everything. 615 Field Squadron Royal Engineers and attached companies execute the construction under continuous harassment. German batteries are logged in Army Group West messages. 15 artillery pieces ranging from 75mm to 150mm registered on the crossing site. Fire is continuous but not concentrated enough to stop construction. Continuous truss over pontoons, a hybrid system combining Bailey panels with floating supports. Bank seats reinforced with piles driven through mud to firm clay. cribbing with salvaged timber and stone. Each pontoon section anchored against current. Each truss section locked to the next. The work progresses in stages. Bank approaches first, excavation and grading under mortar fire. Abutments second, cribbing and pile driving under artillery fire. Pontoons third, positioned by boat crews under small arms fire from the far bank. Trusses fourth, assembled and launched under sustained shell fire. Traffic reaches approximately 3,000 vehicles per day by August 27th. The count is meticulous. Military police log every vehicle. Tanks at 0600 through 0800. Supply lorries 0800 through 1200. Fuel tankers 1200 through 1600. Ambulances and recovery vehicles 1600 through 2000. Artillery and heavy equipment 2000 through 2400. The cycle repeats daily. The structure remains functional for 3 months until replaced by a permanent span in November. Minor repairs are continuous. Deck chesses replaced weekly. Pontoon anchors adjusted daily. Panels inspected hourly. The bridge is maintained as carefully as it was built. 2nd Army Engineer War Diary, Vernon Crossing Annex, documents the timeline in minute detail. Every stage recorded. Every delay noted. Every casualty logged. German signal summary, intercepted by ultra-decryption, notes bridging tempo unmatchable. The word appears in the decrypt dated August 28th. German engineers cannot keep pace with Allied bridging. They destroy one span. 2 appear. A river line designed to pause an army becomes a brief cue for traffic control. Convoy space at 30-yard intervals to reduce casualties from shellfire. Military police direct traffic with timed precision. Engineers maintain the deck with constant patrols. Artillery suppresses German observers on the far bank. Air support interdicts German reinforcements moving toward the crossing. Within days, Allied forces cross at 6 points along the Seine. Vernon, Les Andelys, Mantes Gassecourt, Poissy, Conflans, and others. The German timetable collapses upstream and downstream. Each crossing site becomes a supply artery. The retreat accelerates into route. Paris is days away, liberated August 25th by French forces, secured August 26th by Allied columns. The Vernon Bridge alone passes approximately 3,000 vehicles daily for 90 days. Total, approximately 270,000 vehicles. Multiply that by 6 crossing sites. Approximately 1.6 million vehicle crossings in 3 months. Armor, artillery, ammunition, fuel, rations, replacements, medical supplies, mail. Everything an army needs to maintain pursuit across an entire country. Germany expected the Seine to buy time measured in days or weeks. Britain gave Germany a traffic jam measured in hours. The Wehrmacht retreats not because it is defeated at Vernon, but because it cannot prevent what Vernon represents. Unstoppable mobility. Bridging faster than demolition. Construction faster than destruction. Engineering faster than war. The arithmetic is absolute. Germany destroys 1 bridge per day. Allies build 6 bridges per day. Germany interdicts 1 crossing per week. Allies open 12 crossings per week. The mathematics of industrial warfare overwhelm traditional military doctrine. By August 27th, the Seine is behind the Allies. Ahead, Belgium, the Netherlands, the West Wall, Germany itself, and at every river, every canal, every blown culvert, the same pattern will repeat. Reconnaissance, survey, materials, assembly, traffic, next crossing. The Bailey Bridge at Vernon is not the largest structure of the war. It is not the longest span. It is not the most heavily trafficked. But it represents a principle proven from Africa to Italy to France. Mobility maintained despite opposition. Geography erased by engineering. Strategy enabled by logistics. Victory built by hand, panel by panel, pin by pin. A convoy board shows Priority Well, Antwerp. A sapper sergeant tallies bridge serials, 47 through 96. The date is September 1944. Brussels-Antwerp axis. Belgium is liberated. Germany is retreating. The bridges are everywhere. Mobility is absolute. German retreat demolishes highway and rail bridges systematically. Every major crossing blown. Every minor culvert destroyed. The demolition plan is comprehensive. Deny the Allies every road, every route, every shortcut. Allied planners expect week-scale delays based on conventional bridging capacity. Reality proves otherwise. SHAEF Engineer Branch Report E/10, compiled in October, later summarizes 96 Bailey bridges in 15 days, averaging 6.4 bridges per day, maintain approximately 8,000 vehicles per day flows across the entire theater. The statistics are staggering. 96 bridges, 15 days, 0 structural failures. 2nd Canadian Corps engineers work near Antwerp approaches. 23 bridges in the port sector alone. British 2nd Army Royal Engineer groups span inland rivers. 38 bridges supporting the advance toward the Netherlands. United States 1st Army Engineers on the southern flank. 35 bridges maintaining supply lines toward Aachen. The coordination is seamless. The execution is universal. German rearguards operate with limited explosive stores. Allied air interdiction has destroyed supply dumps throughout France. Wehrmacht engineer companies retreat faster than explosives can be distributed. Some bridges are blown with improvised charges, inadequate and incomplete. Other bridges are abandoned intact. No time, no materials, no options. Rapid surveys become doctrine. Reconnaissance elements reach a blown bridge. Engineer reconnaissance teams arrive within 30 minutes. Survey complete within 1 hour. Materials requisition transmitted immediately. Bailey components arrive within 3 hours by prepositioned supply columns. Assembly begins within 4 hours. Traffic opens within 10 hours. The cycle is mechanical, predictable, unstoppable. Modular abutments speed construction. Prefabricated cribbing. Standardized approaches. Templates for bank preparation. Everything designed for speed. Everything tested under fire. Everything proven across 2 years of combat operations. Night launches become routine. Darkness protects against air observation, though German air power is nearly extinct by September. Work lights are carefully shielded. Crews work in sections with overlapping shifts. Fatigue is managed through rotation. Efficiency increases through practice. Double-double and triple-single configurations for increasing loads. Sherman tanks require Class 40 minimum. Churchill tanks demand Class 50. Heavy tank destroyers need Class 60. The engineers know the load tables by memory. They adjust configurations on site based on requirements. The engineers work faster than German demolition teams can destroy. The principle is proven repeatedly. For every span blown, 2 Baileys appear. The ratio is consistent across the theater. Germany demolishes 1 bridge. Britain builds 2 bridges. Germany demolishes 3 bridges. Britain builds 7 bridges. The multiplication is relentless. Canadian Army Engineers reports from September 1944 document the pace with precision. Bridge locations mapped. Construction times logged. Traffic counts recorded. German demolition logs, captured in November, show shortages of explosives and detonators. But by then the campaign is beyond recovery. The retreat is faster than supply can support. Wehrmacht units withdraw faster than engineer companies can prepare demolitions. Command breaks down. Communication fails. Units bypass planned demolition sites. Bridges that should be destroyed remain standing. The collapse accelerates. Mobility leaps ahead of German reorganization. Allied columns advance faster than German staffs can plan responses. The tempo overwhelms defensive calculations. Antwerp's capture on September 4th opens the greatest port in Europe, but only if the roads leading to it remain open. The Bailey bridges keep the roads open. Antwerp itself requires extraordinary engineering. The port is intact, captured before major demolition. But the approaches are destroyed. Every bridge blown. Every overpass demolished. 2nd Canadian Corps engineers rebuild the infrastructure in days. 23 Bailey bridges in the port sector. Traffic flowing by September 10th. The port operational by September 28th after mine clearance. For each blown span, 2 Baileys appear, an inversion of attrition that the retreat cannot reverse. Germany's defensive strategy depends on demolition creating delay. Allied operational strategy depends on construction erasing delay. The contest is unequal. Industrial capacity defeats tactical innovation. The engineers become the vanguard of liberation. Belgian civilians watch Bailey bridges appear overnight. Children count the panels. Women bring coffee to work crews. Men offer to help, untrained but willing. The bridges represent more than military engineering. They represent freedom restored, commerce renewed, normal life returning. By September 18th, 96 Bailey bridges span Belgium. From the Scheldt to the Meuse, from the coast to the Ardennes. Every major route, every secondary road. None have failed. All carry traffic. The liberation of Belgium is a logistics achievement as much as a military victory. And the logistics depend on bridges, thousands of tons of prefabricated steel, assembled by hand under pressure, faster than the enemy can respond. Germany's retreat is a race between demolition and construction. In Belgium, September 1944, construction wins decisively. The bridges stand. The traffic flows. The advance continues without pause. The momentum builds toward the final frontier, Germany itself. Fog sits on the Vaal River. A field company lays out pontoons while a clerk pencils P.S. flood risk. Add bays. The date is September 21st, 1944. Market Garden has failed at Arnhem 70 miles north. 1st British Airborne Division is trapped, then evacuated. But supply lines must hold. The corridor must remain open. A temporary Bailey near Nijmegen is erected by 615 Field Squadron Royal Engineers in approximately 8 hours, record time under difficult conditions. The bridge sustains crossings for 504th Parachute Infantry Regiment elements and follow-on traffic. American paratroopers crossed the Vaal by boat in one of the war's most desperate actions. Now they need supplies. The bridge provides. Flood waters force extensions by floating bays overnight. The Vaal rises suddenly. Autumn rains upstream in Germany. Engineers add pontoon sections to the original fixed-span design. The hybrid structure grows organically. Fixed spans on the banks. Floating spans in the current. Each section adjusted to water levels. 30th Corps engineers coordinate with United States forces in unprecedented multinational cooperation. Engineer parks supply both armies from common stockpiles. British panels fit American transoms. Canadian chesses fit Polish rollers. Standardization proves its worth. A Bailey bridge is a Bailey bridge regardless of who builds it. German artillery firing tables adjust for bridge targets repeatedly, but the bridges adapt faster than the artillery. Observers on the far bank report coordinates. Batteries fire concentrations. Engineers assess damage. Repairs begin immediately. Traffic resumes within hours. The cycle repeats but never stops. Hybrid fixed floating sections challenge engineering doctrine but work effectively. The fixed spans provide stability. The floating spans provide flexibility. Water rises, pontoons rise with it. Water falls, pontoons adjust. The design accommodates nature while maintaining function. Deck relaying under fire becomes routine for the crews. Shells damage chesses. Sappers replace them section by section. Traffic pauses for 5-minute intervals. Vehicles wait. Engineers work. Traffic resumes. The bridge never closes completely. Partial capacity is maintained continuously. Traffic control points maintain spacing to protect against direct hits. Military police space vehicles at 50-yard intervals. One shell cannot destroy multiple vehicles. One hit cannot close the bridge. The doctrine evolves from experience. Protection through dispersion. 30th Corps Engineer Diary and United States Army After-Action Reports from late September document the work in parallel formats. British Military Time. American Standard Time. Different formats. Same facts. 18 Bailey bridges in the Nijmegen salient by September 30th. all functional despite German artillery, autumn floods, and operational chaos. German artillery diaries, captured in March 1945, note with frustration. Enemy bridges in operation despite high water. The notation appears repeatedly. September 22nd, bridges operational. September 24th, bridges operational. September 27th, bridges operational. Every assessment the same. Every result the same. Even when the operational plan fails, the engineering network preserves a viable front and prevents collapse. Arnhem is lost. 1st Airborne Division withdraws across the Rhine with terrible casualties. But the Nijmegen bridges remain. The corridor holds. The front stabilizes. Winter positions are established. The failure is operational, not logistical. Arnhem did not cut the artery. Bailey spans kept the logistics alive for winter operations. Germany expected Market Garden's failure to collapse the Allied position in the Netherlands. German commanders anticipated retreat, withdrawal, defensive adjustments back to Belgium. Instead, the engineers maintained a salient, supplied forces across the Waal, and prepared for the next offensive. The Betuwe Island between the Waal and Rhine becomes a staging area for subsequent operations. Supplies flow across Bailey bridges continuously. Artillery positions receive ammunition by the truckload. Infantry replacements reach forward units by the company. Medical facilities treat casualties without interruption. The infrastructure sustains operations despite tactical failure. Supplies flow across Bailey bridges that are shelled daily but never destroyed permanently. Damage is continuous. Repair is constant. The balance favors repair. German artillery has limited ammunition. Allied engineers have unlimited panels. The arithmetic is absolute. A German intelligence summary from October, intercepted by Signals Intelligence, notes Allied bridging, unaffected by operational setbacks, unaffected. The word is precise. The battles may be won or lost, but the bridges remain. Logistics continues. Supply flows. The infrastructure holds regardless of tactical outcomes. The distinction matters strategically. Tactical failure at Arnhem does not create strategic crisis. The front holds because logistics holds. Logistics holds because bridges hold. Bridges hold because engineering is systematic, industrial, and unstoppable. By September 30th, the Nijmegen bridges have carried thousands of vehicles, tens of thousands of soldiers, and uncounted tons of supplies. The offensive failed. The bridges succeeded. And that distinction preserves Allied positions for winter operations and eventual spring offensives into Germany. The lesson is stark. Superior engineering creates operational resilience. Battles can be lost. Offensives can fail. But if logistics remains intact, the war continues. And if the war continues, eventual victory becomes mathematical. Industrial capacity, trained personnel, standardized equipment, systematic execution, all focused on a single principle: sustained mobility despite opposition. A night panorama of work lights. Cranes swing crates of panels. A notice board reads Blackfriars, Class 40, convoy distance enforced. The date is March 24th, 1945. Lower Rhine bridgeheads, Ries and Wesel, the last major natural barrier before the North German plain. The last natural line Germany can hold. The Rhine is the final shield, Germany's greatest river. 800 feet wide at Ries. Current, 4 miles per hour. Depth, 15 feet minimum. Banks, fortified since autumn 1944. Defenses in depth. Observation posts. Artillery registered on every approach. The plan is absolute defense. German artillery commands project days of interdiction based on previous campaign experience. Doctrine suggests minimum 1 week to establish a crossing strong enough for sustained operations. British 12th Corps engineers complete the Blackfriars Bailey, approximately 1,470 feet, in approximately 3 days. From first pontoon to traffic opening. 72 hours. Reality defeats doctrine. Traffic. Approximately 8,000 vehicles per day, once fully operational. Materials: thousands of tons of Bailey panels, transoms, chesses, pontoons by the hundreds, anchoring cables by the mile. Manning: approximately 1,500 engineers in rotations. 8-hour shifts, continuous work, day and night. The construction never stops. Royal Engineers Corps troops execute the work. Specialist bridging companies supplemented by divisional engineers. 12th Corps operations logs track progress section by section, hour by hour. German Artillery Command 11 notes reserves arrive late to the sector, delayed by air interdiction and fuel shortages. The planned artillery concentrations never materialize at full strength. Multi-bay continuous truss on pontoons, the longest Bailey bridge yet constructed under combat conditions. Each bay, approximately 100 feet. 14 bays total. Pontoons spaced for current and load. Anchors set upstream and downstream. Each anchor cable, 3-inch diameter steel. Each anchor point, surveyed, marked, recorded. Multiple approaches to distribute traffic and provide redundancy. Northern approach for armor and heavy vehicles. Southern approach for supply and administrative traffic. Center approach reserved for priority movements. The system prevents bottlenecks and distributes risk. Redundancy for panel damage built into the design. Extra bays installed for strength. Backup panels staged on both banks. Repair crews on standby 24 hours. When a section is damaged, replacement happens immediately. Traffic never stops completely. Constant deck maintenance under operational conditions. Engineers walk the bridge hourly, checking pins, inspecting transoms, testing chesses. Minor repairs happen continuously. Major repairs happen during scheduled traffic pauses. 2 hours per day at 0300 to 0500 when volume is lightest. Anti-aircraft guns protect the site from air attack, though Luftwaffe is nearly destroyed by March 1945. Smoke generators obscure observation during daylight, chemical smoke from generators positioned upwind. Artillery observers on the far bank cannot acquire targets through the smoke. Counter-battery fire suppresses German guns when they reveal positions. British Corps Engineer After-Action Report from March 1945 documents the construction with photographs and technical drawings. Air photo mosaics show progressive completion. Images taken every 6 hours show the bridge growing across the river. The bridge grows across the Rhine like a steel road, section by section, bay by bay, meter by meter. The Rhine ceases to be a shield the moment traffic opens. Armored and logistic traffic flood into the North German plain. The Ruhr is encircled by April 3rd. Berlin becomes the target. Germany's last geographic advantage evaporates under the weight of Allied engineering. Geography no longer dictates strategy. The last line breaks not by storm boats alone, but by a factory-made truss pushed into place faster than artillery can stop it. Assault troops cross by boat at 0200, March 24th. Engineers begin bridging at 0600. First armor crosses at 1400, March 26th. Full traffic flow by 1800, March 27th. The sequence is mechanical, inexorable. German defenders shell the bridge continuously from positions across the North German plain. Panels are hit by 105 mm and 150 mm high explosive. Deck sections are damaged by near misses and shrapnel. Engineers replace them section by section. Traffic pauses for 5 to 10 minutes per repair. Repairs happen under fire, no different from Italy, France, Belgium. The drill is practiced. The execution is automatic. A German prisoner from a Wehrmacht engineer company, interviewed on April 2nd, states, "We could hear them building all night. We shelled them all night. In the morning, they were still building all night. Continuous. Unstoppable. The bridge as inevitability." The prisoner's tone is not hostile. It is resignation. The war is ending. Everyone knows. By March 28th, the Blackfriars Bridge is complete and traffic is flowing at maximum capacity. The Rhine is behind the Allies. Ahead, Hanover, Magdeburg, the Elbe, Berlin. The end of the war in Europe. And at every river between the Rhine and Berlin, more Bailey bridges will appear. The pattern is established. The system is proven. The result is certain. A stack of used panels stamped with varied contractor marks. London, Birmingham, Glasgow, awaits redeployment. The date is April 1945. Northwest Europe, the final month of the European War. Bridges are everywhere. German planners counted on rivers and demolitions to impose operational pauses. War Office reviews note more than 3,000 Bailey bridges in European service by May 1945. Cumulative spans, dozens of miles. Total tonnage, hundreds of thousands of tons. Structural failure rate, less than 1%. War Office Historical Section and SHAEF G4 Logistics Branch compile the statistics. 3,000 bridges. From Normandy to the Rhine. From Belgium to the Elbe. Every river. Every canal. Every bombed-out culvert. Standardization created a bridging economy, interchangeable parts. Predictable training. Pre-packed loads. Proven drills. German bridging capacity shrank under bombing and resource scarcity. Comparable modular systems were not fielded at scale. War Office post-campaign survey documents the advantage. Captured German engineer production returns from 1943 through 1945 show approximately 40% drop in output. German bridging relies on heavy equipment, rail transport, and specialist crews. Allied bridging relies on standardized panels, truck transport, and unit-level training. Every enemy demolition becomes a brief engineering task. The Allied timetable becomes the only timetable. Germany blows a bridge at 0800. Allied engineers arrive at 0900. Survey complete by 0930. Assembly begins at 1000. Traffic opens at 1400. Next bridge. The pattern repeats across an entire theater. Hundreds of times. Thousands of times. Every blown span becomes an appointment on the engineer's calendar. Every demolished crossing becomes a 6-hour delay, not a 6-day crisis. Air superiority dominated the sky. Artillery dominated the battlefield. Armor dominated maneuver. Bailey bridges made mobility a ground-level equivalent. The combination was overwhelming. Germany could not retreat faster than the Allies could bridge. Germany could not demolish faster than the Allies could build. Germany could not interdict faster than the Allies could repair. The arithmetic was absolute. By May 1945, the war in Europe ends. The Bailey bridges remain. Traffic continues. Refugees return. Displaced persons move. Supply convoys roll. Occupation forces deploy. The bridges transition from war to peace without pause. The date is June 1946. London. The honors list. The war is over. The recognition begins. Temporary wartime expedient becomes long service standard. Variants appear in Korea, Vietnam, Somalia, Afghanistan. Civilian emergencies worldwide reuse military stock. The Bailey outlasts the war that created it. Ministry of Supply, United Nations Relief and Works, post-war firms, maybe and others, continue modular truss bridging concepts. Calendar Hamilton and other systems share the kit bridge ethos. The design logic persists. The Bailey's design logic, panels, pins, transoms, standardized logistics, remains the baseline for emergency and expeditionary bridging. A 1950 United Nations Engineering Review calls it the most successful temporary bridge design yet produced. London Gazette Honors Publication. United Nations Technical Reports from the 1950s. British Army equipment schedules showing continued service into the late 20th century. The Bailey serves for decades. A wartime invention intended to save days in battle ends up saving months in reconstruction and disaster relief. Earthquakes, floods, typhoons, hurricanes. Wherever infrastructure collapses, Bailey bridges appear. Humanitarian agencies stockpile panels. Military forces maintain inventories. The system is universal. Korea, 1950 through 53. Baileys span the Han River, the Nakdong, the Imjin. Vietnam, 1960 through 75. Baileys replace bridges destroyed by war. Somalia, 1992 through 93. Afghanistan, 2001 onward. The same panels. The same system. Generations of conflict. One solution. The genius was not complexity. The genius was simplicity. Panels that fit together with pins. Transoms that slot into brackets. Decking that lays on rollers. No welding. No cutting. No specialized tools. Just steel, geometry, and trained crews. Donald Coleman Bailey received his knighthood in 1946. He lived to see his bridge used on every continent. He died in 1985, aged 83. His invention outlived him by decades and continues in service worldwide. Where armored divisions advanced, a Bailey had already provided the road. Built in hours, bearing the weight of a war and the recovery that followed. From Sangro to the Rhine, from Tunisia to Berlin, from Normandy to the Elbe. Everywhere the Allies went, the Bailey went first. The Bailey Bridge was not the largest weapon of World War II. It was not the fastest, nor the most powerful, nor the most destructive. It was simply the most effective at the one task that mattered most. Keeping armies moving. 3,000 bridges. Dozens of miles of span. Hundreds of thousands of tons of steel. Assembled by hand, under fire, faster than the enemy could respond. The numbers are overwhelming. The principle is simple. Germany's strategy relied on geography, rivers, mountains, demolitions to slow the Allies. Britain's strategy relied on engineering to erase geography. In that contest, engineering won. Not once, not twice, every single time. The lesson of the Bailey Bridge is not about technology. It is about systems, standardization, training, logistics, industrial capacity, democratic mobilization, all applied to a single purpose. Mobility maintained despite opposition. The soldiers who built the bridges rarely receive recognition. They worked at night under shellfire, in rain and mud and cold. They carried 570-kilogram panels across rivers. They assembled trusses while snipers fired. They repaired spans while artillery ranged. The engineers were not heroes in the traditional sense. They were technicians, builders, problem solvers. But their work enabled every advance, every offensive, every victory. Without them, the war would have lasted longer, cost more, and ended differently. Today, Bailey bridges still serve. In disaster zones, in refugee camps, in remote areas without infrastructure. The design is 85 years old. The principle remains sound. The system still works. Donald Coleman Bailey's invention changed modern warfare. It made mobility faster than demolition. It made engineering a weapon as decisive as air power or armor. It proved that wars are won not just by soldiers, but by the systems that support them. The Bailey Bridge is a monument to the idea that simple solutions, executed at scale, can change history. It is a reminder that engineering is strategy, that logistics is power, that the unglamorous work of building infrastructure wins wars as surely as battles do. The bridges are mostly gone now, replaced by permanent structures, scrapped, recycled, but the principle remains, and the memory endures. What is your perspective on this part of history? Share your thoughts in the comments, because every memory and reflection helps keep the past alive.